Now we will discuss about thermal resistance concept. Thermal resistance concept. Consider a pen wall of thickness delta L, or we can say the thickness is L. The left hand surface is maintained at temperature T1 and the right hand surface is maintained at temperature T2. And if the heat conduction through the wall is a steady state, then the heat conduction rate of heat conduction through wall is given by, and if we are saying conduction is in this direction, then Q dot conduction is given by Ka T1 minus T2 upon L, where A is the surface area of the wall and K is the thermal conductivity. Thermal conductivity of the material. This equation can be written as T1 minus T2 upon L upon Ka, or we can write it as T1 minus T2 upon R conduction, where R conduction is known as the conduction resistance If we see the equation 1, it is analogous to Ohm's law, which is the current I is a voltage drop over electrical resistance. If we compare these two equations, we say T1 minus T2 corresponds to voltage drop, Q dot conduction corresponds to electrical current, and RE, R conduction, corresponds to electrical resistance. So, if we have a ball whose conductance resistance is known, then we can draw an electrical network. This is R conduction and this surface is maintained at temperature T1 and T2. This is known as the electrical circuit of conduction resistance, and Q dot conduction is given as T1 minus T2 on R conduction, where R conduction is equal to thickness of the wall over product of thermal conductivity and surface area. So, the conductance resistance for wall is given as L by Ka. Conductance resistance for a cylinder is given as ln of R2 upon R1 upon 2 pi Kl, and conduction resistance for a sphere is given as R2 minus R1 upon 4 pi K R1 R2, where R1 R2 are inner and outer radius respectively. K is the thermal conductivity So let us say if this is a cylindrical cell, then this one is R1 and this one is R2. R1, R2 is nothing but the inner radius and outer radius. Similarly, for a spherical, this is the cylindrical cell. Similarly, for a spherical cell. Let us say this is R1 and this is R2, then this is the inner radius and this is outer radius, R2, outer radius, and conductivity of this material is K, and one term L is coming in the conduction resistance of cylinder, that L is nothing but the L is length of cylinder. Okay, so the electrical analogy of resistance for a sphere will be E1, E2, and this one will be R conduction cylinder is equal to ln of R2 upon R1 upon 2 pi Kl. Let us say this is Q dot conduction for a cylinder, then Q dot conduction for a cylinder is given as T1 minus T2 upon R conduction cylinder. Similarly, the electrical analogy of thermal resistance for a sphere will be T1 T2, and R conduction of the sphere is given as R2 minus R1 upon 4 pi K R1 R2, and the heat conduction through a spherical system is given by Q dot conduction through a spherical cell is T1 minus T2 upon R conduction is spherical. This is important. This one is also important. So remember this. And the other one is the wall. Now consider a plane wall for any body. The surface area is A and surface temperature is Ts, and a fluid whose free stream temperature is T infinity. Since here is a temperature difference between the wall and the fluid, so there will be some amount of heat convection from surface to fluid or fluid to surface, depending upon the temperature difference Ts and T infinity. Either it is greater than 0 or less than 0. If T infinity minus Ts is greater than 0, that means heat is flowing from fluid to surface, and if T infinity minus Ts is less than 0, heat will flow from surface to fluid. And the mode of heat transfer here is convection, because mode of heat transfer is convection due to bulk motion of fluid. So, the rate of heat transfer is given by Newton's law of cooling for convection heat transfer. Remember this. So Q dot convection is H A is Ts minus T infinity, right? Or we can write this as T infinity minus Ts, depending on which quantity is greater. So I can write this as Ts minus T infinity upon 1 upon Hs, Q dot convection. Or I can write this as T minus T infinity upon R convection, where R convection is given as 1 upon HAS and known as convection resistance. If we compare the equation 3 with Ohm's law, that is, electric current I is voltage drop upon electrical resistance. So, R convection corresponds to electrical resistance in electrical analogy. So, if this is the wall and the surrounding fluid is at temperature T infinity, so there will be one heat transfer, and the electrical resistance or electrical analogy of heat transfer can be given as this network. This is R convection. If we know convection resistance, then we can find out the convective heat transfer between fluid to surface or surface to fluid, depending upon the temperature. So Q dot convection can be given as T infinity minus Ts or Ts minus T infinity upon R convection. The important thing here is R convection is 1 over product of HA, where H is the convective heat transfer coefficient Till now we have discussed the heat transfer through conduction only, and we were neglecting the heat transfer due to convection on the surface of a wall. Let us say this is a wall of thickness L, and its surface is subjected to convection on both sides. Let us say the fluid temperature on left hand side is T∞1 and the fluid temperature on the right hand side is T∞2, and the convective heat transfer coefficient between fluid and surface, left hand surface, is H1, and this convective heat transfer on the left hand side is H2. In this case, how the heat will flow? So there will be one heat transfer from fluid to wall, that is due to convection, and this heat will flow into the wall due to conduction, and again this heat will be lost to the surrounding via convection. At the interface of fluid and surface, there is some convective resistance. So if we want to draw the thermal resistance diagram for this situation, its temperature is T∞1. Let us say the left hand side wall surface is maintained at temperature T1. So this node will have temperature T1, and this wall is offering some conduction resistance. Let us say our conduction wall, and this conduction is due to convection, so let us say this is our convection 1. Now the wall is offering some conduction resistance, our conduction wall, and its temperature, wall temperature, has dropped to T2 on the right hand side surface. Again at this surface there is one convection resistance on the right hand side that will cause the temperature drop, and as we know, the right hand side fluid temperature is given as T∞2, and this resistance, convection resistance, is, let's say, convection 2. So here our convection 1 is nothing but 1 by H1A, where A is the surface area of this wall. A is surface area. Our convection 2 is 1 by H2A on right hand side, and our conduction wall, as we have discussed earlier, is nothing but L upon Ka, where K is the thermal conductivity of this wall. So if we want to get what's the amount of heat that is flowing through this wall, if we know the resistances, convection and conduction resistance of this arrangement, and we know the fluid temperature on both sides, so this can be given as T∞1 minus T∞2 upon R convection 1 plus R conduction wall plus R convection 2. So this is the amount of flow or heat that is flowing through the wall. Rate of heat transfer through wall under steady state, right? From the electrical analogy, we can write this Q dot as T infinity 1 minus T1 upon R convection 1 is equal to T1 minus T2 upon R conduction of wall is equal to T2 minus T infinity 2 upon R convection of 2. This is equal to T infinity 1 minus T infinity 2 upon R convection 1 plus R conduction wall and so on. And this is finally is equal to T infinity 1 minus T infinity 2 upon R convection 1 plus R conduction wall plus R convection 2. So if you see this relationship, if you know the T infinity 1, T infinity 2, H2 and H1, and you know the resistances R convection 1, R convection 2 and R convection 2 and R conduction 1, then you can find out the rate of heat transfer. Once you have the rate of heat transfer, you can find out the surface temperature T1 and T2 from this relationship. So, if we knew the fluid temperatures and thermal resistance, we can get the surface temperature T1 and T2. And the other important thing here is thermal resistance follows all the rules of electrical resistance. That is, if thermal resistances are in the series, let us say there is two thermal resistances, then we can replace it with the equivalent resistance of R1 plus R2, R equivalent. This is resistance in series. If two resistances are in parallel, then the equivalent resistance is given as, let us say this is R1 and R2, this is in parallel. So equivalent resistance R equivalent is given as R1 R2 upon R1 plus R2. This is known as resistance in parallel combination. Now we will discuss multi-layer walls. Multi-layer walls, that is, when a wall is made of more than two different layers, then we call it as a multi-layer wall. Let us say a wall is made of three interiors. Those thermal conductivities are K1, K2 and K3 respectively. Length, that means thickness, is L1, L2, L3 and surface areas are same. Okay. And the outer surface of the wall is doing some convection from the surrounding on the left hand side, and the fluid temperature is T1 and corresponding convective transfer coefficient is H1. Similarly, on the right hand side, the fluid temperature is T2 and the convective heat transfer coefficient is H2. So, in this case, all these layers are in series. Layers are in series. So, the thermal resistance or conduction resistance R1 is given as L1 upon K1A, R2 is L2 upon K2A, and R3 is L3 upon K3A. So, the thermal resistance network for this series can be drawn as, this is the convection resistance or convection 1, which is nothing but 1 by H1A, first conduction resistance, second one, third one, and then again convection resistance. This is T∞2, this is T∞1. Let us say this temperature, this surface temperature is T1, at the interface of 1 and 2 is T2, at the interface of 2 and 3 is T3, and the right hand side surface temperature is T4. So this is T1, this is T2, this is T3, this is T4. This is nothing but R1, R2, R3, and this is again R convection 2, which is 1 by H2A. Since all these resistances are in series, so R equivalent is nothing but R convection 1 plus R1 plus R2 plus R3 plus R convection 2. So, what will happen if instead of a plain wall we have a multi-layer cylindrical cell? Consider a cylindrical cell. Let us say this is my cylindrical cell. Another surface is here. R1, R2, R3. This is made of two cylindrical cells. One is of the radius R2 and R3, and the another one is R1 and R2. So, if we say in the inside surface, on the inner surface of the cylinder, some amount of convection is taking place between surrounding air or air and the surface, and the convective heat transfer coefficient is H1 and the fluid temperature there is T∞1. Similarly, the surrounding air temperature outside of the cell is T∞2 and convective heat transfer is H2. Since these two cylindrical surfaces are in series, so when we draw the electrical or thermal resistance diagram, we will have one convective resistance, other one conduction resistance for inner cell, conduction resistance for outer cell, one more convection resistance. Let us say this is R convection 1, this is R1, this is R2, this is R convection 2. Where R1 is the conduction resistance of inner cell, which is given as we know R1 upon R2 upon 2 pi K1L. Let us say the thermal conductivity of inner shell is K1. And the R2 is given as ln of R3 upon R2 upon 2 pi K2L, where K2 is the thermal resistance of outer shell. In that case, and we know the inner fluid temperature, outer fluid temperature, so the Q dot flowing from inner surface to the outer surface, this can be given as T infinity 1 minus T infinity 2 upon R convection 1 plus R1 plus R2 plus R convection 2. The same formula holds good for the spherical cell.